For the last two parts of this section, we need to draw evolutionary paths of stars on an HR diagram and also look at pulsars or neutron stars. Here we have an HR diagram, and we'll just look at a star which basically has a G star. It has an absolute magnitude like our Sun, so it's like the Sun. So it burns for most of its lifetime the hydrogen on the main sequence section here. Then as it uses up the hydrogen, the core will start to contract, the outside will swell, and it moves to this side here. The core contracts and contracts, then helium will start burning here. This is called the helium flash. And so you have shells of hydrogen and helium burning with a carbon stage, and then as that gets used up, then it swells again and becomes a red giant, super red giant here. And then suddenly the outside drifts off into space, becomes a planetary nebula, and then from here it just moves around here very, very quickly to be a white dwarf. So the last section, the section in red, happens very quickly indeed. Here's another graphic which shows what happens to the radius at different points here. So this is main sequence. It starts to drift off the main sequence here as the hydrogen gets depleted, and then it becomes a red giant. And this is a bit simplified actually. Then it becomes a helium flash where the helium will start to burn, and it goes on to what's called the horizontal branch, and it will stay there for a while. Then the helium will be used up, and it will move higher up again here to a brighter star as it enlarges. Here we have the paths of different stars. This is a sun, which we've looked at here. There's a helium flash, the horizontal branch, and then because it becomes a giant, a supergiant. If we have a star which is 5 solar masses, it's much more horizontal, the path here, but basically it does the kind of same thing here. And a 10 mass star, 10 solar mass star, moves across to the supergiant straight away, and then starts to produce carbon and oxygen and so on. And then of course after each of these, in this case for example 10 molar mass, this will become a supernova. This will happen at this point here, and then very quickly it will become a neutron star, so it becomes very, very dim afterwards. So what is a neutron star? The remnant of a supernova, remember when it's greater than 1.4 solar masses of the core, the remnant of the supernova is composed basically of entirely of neutrons, because we've overcome this electron degeneracy, but we can't go beyond this. We have this thing called the neutron degeneracy, which stops the neutrons being crushed into each other. So the white dwarfs, which we looked at before, are the size of planets. Neutron stars are the size of towns. That's how compact they have become. They also spin very quickly, and when they spin, they become pulsars. We see them as pulsars. So nuclei, as we know them, cannot exist. We just have solid neutrons. The outer envelope is about a mile thick, and it's just nuclei and electrons in the outer shell, outer crust. The neutron, the pulsar, is here. It spins on this axis, but the radio beams are emitted on this axis. So as it spins round, the beam of the radio beam spins round like a bit like a lighthouse.